everybody. My name is Meghna. I'm a final year PhD student from Macquarie University under the supervision of Dr. Devika Kamath. So today I'm going to talk about my latest publication with the research question, do intrinsically S-process enriched evolved binaries exist? Binary stars can display a diverse range of chemical signatures arising from strong yet poorly understood interaction with their companion. So far, the well-studied sample of low to intermediate mass binary stars that display S-process enrichment are typically extrinsic. This means that they have been polluted by their evolved companion. Examples of these include barium stars, carbon-enhanced metal poor S stars, and extrinsic S stars. You will or would have heard about these stars during the conference. So these extrinsically enriched binary stars showcase an unevolved primary star like a main sequence star paired with an evolved companion like a white dwarf that was a former AGB which produced the S process and transferred it to the main sequence stars as they evolve. However, in my study, we have compiled for the first time a sample of post-asymptotic giant branch binary stars that are S-process enriched, and here the enrichment nature is more likely intrinsic compared to the typical extrinsic nature. So in today's talk, I will highlight the chemical peculiarities of the targets and also talk about the potential nature of their enrichment. Now, before getting into the target details, I would like to give a quick overview and point out some important aspects with respect to post-AGB stars. So post-AGB stars are nothing but evolved AGB stars. And here's a schematic representation of a single post-AGB star surrounded by a dusty circumstellar envelope. The spectral energy distribution of single post-AGB star has a double peak SED, where the first peak represents the photospheric flux, and the second represents the infrared excess from the circumstellar envelope. The single stars are known as shell sources. Now, as you can see in the abundance plot here, majority of the single post-AGB star has a photospheric chemistry, which is a reflection of their AGB nucleosynthesis, like dredge-ups, hot bottom burning, carbon and S-process enrichment. Now, things can get very different and complicated when there is a companion. So in the case of binary post-AGB star, which was discussed in detail by both Maxime and Katharina during their talks yesterday and today, here is a schematic representation of a binary post-AGB star with the primary post-AGB star and the secondary companion being a main sequence star with bipolar jets and it's surrounded by a circumbinary disk of gas and dust. Now, the spectral energy distribution as well as the photospheric chemistry of binary post-AGB stars are very different from that of singles, as you may have noticed. Binary post-AGB stars are known as disk sources with a broad infrared excess, which is indicative of the circumbinary disk surrounding the system. And unlike single stars, we do not see in the photospheric chemistry of binary post-AGB stars, the expected S-process enrichment. This is because majority of the binary post-AGB stars has this chemical anomaly that Maxime just discussed, which is known as photospheric chemical depletion, where we see an underabundance of refractory elements, including majority of the S-process elements. So coming back to the target of our study, the target of the study was compiled using a combination of both photometry and spectroscopy. Coming to the photometry part, this is a wise color diagram used to distinguish between the shell sources and the disk sources. So as mentioned previously, disk sources are indicative of the stable circumbinary disk around the system and therefore attributed to binarity, and therefore we expect a depleted photosphere for these systems. However, what makes our targets interesting is that our targets are post-AGB disk sources, but instead of showing a chemical depletion, they show S-process enrichment. And these targets are in the galaxy, LMC, and SMC. The spectral energy distribution of the 3 targets of this study are shown here, and one of them is indeed a confirmed binary with orbital period close to 1 year. Now, coming to the spectroscopy part, the high resolution optical spectra of all the targets were from VLT+UVES, and as shown in the spectral snippets here, they reveal signatures of S-process elements. Some of them are marked here, which includes lanthanum, neodymium, barium, cerium, etc. Detailed high-resolution spectroscopic analysis of our targets using our own semi-automated Python wrapper, EISpec, which Maxime just mentioned, further revealed the S-process as well as carbon enrichment for all the 3 targets as shown and marked in the abundance plots given here. Now, in order to understand and investigate the chemical peculiarities of our targets, we compared the photospheric chemistry of the targets with appropriate binary and single post-AGB stars from the literature with similar atmospheric parameters. So this test was done in order to understand if there was a possibility of a mixture of both chemical depletion as well as S-process enrichment in our targets. Taking the case of one of the target as an example, the figure here, the comparison plot here shows that the chemical pattern of the target, not only this target, but all the targets, align consistently with their comparison single stars and not binary comparison star. There is also no signature of a mixture of both chemical depletion and S-process enrichment. It also suggests a possible potential failure in the disk binary interaction inducing chemical depletion in these targets. So why did the disk binary interaction inducing depletion fail for these targets? So in order to explore this, we considered a few scenarios. The first one is it could be because of a difference in depletion efficiencies. It's important to note that for majority of the post-AGB binary systems, the circumbinary disk chemistry is oxygen-rich. Therefore, accordingly, the condensation temperature estimates utilized for this study as well as for previous studies are based on a solar photospheric chemical model, which is, of course, oxygen-rich, and it's taken from Lauders et al. 2003 paper. However, our targets have a photosphere that is enriched in carbon with C/O greater than 1. So this suggests that the depletion efficiencies may be different in a carbon-rich and an oxygen-rich environment. However, condensation temperature estimates specific to carbon-rich or a known solar photospheric composition is required to further look into this aspect. The second scenario that we consider is a potential variation in circumbinary disk morphology around the targets. The circumbinary disk around post-AGB binary systems are classified as full disk and transition disk based on their infrared characteristics. So in order to understand if there was a potential variation in the disk morphology around our chemically peculiar targets, we made use of this color diagram as introduced by Kluska et al. 2022. As seen in this plot, 2 of our targets are full disk and 1 is a transition disk. This suggests that the disk morphology and characteristics of our targets match typical post-AGB binaries. And therefore, the chemical peculiarity of our target is unlikely a characteristics of their disk. Now, moving on to exploring the nature of the enrichment seen in our targets, we considered 3 cases. Case 1, the enrichment being extrinsic from an evolved companion like a white dwarf. Case 2, the enrichment coming from the host galaxy. And case 3, the enrichment being intrinsic from its prior AGB nucleosynthesis. Now, let's look into each of these cases in detail. Case 1, extrinsic. So this is a plot of companion mass distribution function of galactic post-AGB binary stars as studied by Oman et al. 2018. Now, as seen in this plot, the companion mass distribution function peaks at about 1 solar mass. However, the observed distribution of white dwarf mass peaks at about 0.6 solar mass. Additionally, there was no symbiotic activity seen in the spectra of these galactic post-AGB stars. So this suggests that both these statistical as well as observational argument together put in, we conclude that for majority of the post-AGB binaries, it's unlikely that the companion is a white dwarf. Now, as mentioned previously by Katharina, most of the post-AGB binary system launches bipolar jets from the circumcompanion accretion disk, and the jet velocities of these post-AGB binary system ranges between 150 to 640 kilometers per second. Comparing this jet velocity to escape velocity of white dwarf and main sequence, it's more comparable to that of main sequence stars. So this suggests that the companion of majority of the post-AGB binaries are more likely main sequence stars. Now, looking into the case of the confirmed binary target of our study, the dynamical spectral analysis of this target revealed that it has a jet velocity of about 150 kilometers per second. And together with no symbiotic activity observed in the spectrum of this star, we conclude that the companion of this target is more likely a main sequence star. Now, putting all these arguments together and extrapolating it to rest of our targets, we conclude that the observed enrichment of our targets is unlikely extrinsic from the evolved companion, because the companion is more likely a main sequence star. Now, exploring the case 2, which is the enrichment coming from the host galaxy. Literature studies on S-process enrichment of field giant stars suggests that the average intrinsic S-process enrichment of the galaxy as well as the Magellanic Cloud is less than 0.5 degs. However, for our targets, the S-process enrichment, the S over Fe, is greater than 1 degs. This suggests that the observed enrichment of our targets cannot be solely be explained by the enrichment from the host galaxy alone. So we then go to the last case, which is the intrinsic enrichment. For this, we integrated observations with theoretical models following a similar procedure as Kamath et al. 2023. We used a Ton code to model the targets based on the derived luminosity, C over O ratio, and metallicity to predict the AGB evolution of the target based on the assumption that the observed chemistry of the target was a reflection of their prior AGB nucleosynthesis before it was terminated by the binary interaction. Now, we also compare the derived C over O with the observed, the derived C over O with the modeled C over O and the derived initial mass range for the targets. The results from the models predict that our targets have undergone the third dredge-up during the AGB nucleosynthesis, and the observed carbon as well as S-process were produced during their previous AGB phase. Now, the figure here represents the predicted AGB evolutionary tracks over the surface C over O versus luminosity plane for different masses, along with observations for the target J005107 and Macho 47. The gray shaded region and the dashed lines show how well the models match the predictions. The observations match the predictions from the model. The figure on the right shows the time variation of luminosity and C over O for a 2.5 solar mass model star. And the gray shaded region depicts how well the observations of the target HT158616 matches with the predictions from the models. So the results from the models suggest that the evidence of third dredge-up for our targets and therefore a prior AGB nucleosynthesis. And therefore, the enrichment of our target is more likely intrinsic. The key takeaway points that I would like to highlight is that this occurrence is more inclined towards an intrinsic enrichment rather than the usual extrinsic enrichment seen in barium stars, carbon-enhanced metal-poor S stars, and extrinsic S stars. This also suggests that there's a failure of a disk binary interaction inducing depletion in these systems. However, the reason remains unclear. This study also highlights the complexity of binary interaction. I would like to leave you all with some open questions like, why did the disk binary interaction inducing depletion fail in these systems? Why do we only see a small sample of such chemically peculiar targets in terms of post-AGB binary system? And what other characteristics, if any, could be distinct for these targets compared to other binary post-AGB stars? Thank you.
I was a bit curious when you mentioned that there are transition disks and full disks. Are there what are the main differences except for just the size? And are the transition disks really a transition towards the full disks, or are these like earlier post-AGBs? Or
as you may remember from both Maxime's and Katharina's talk, transition disks have this big cavity. I can show the pictures to make it clear. You see, there's a big cavity which is carving the particle away from the start of the disk sublimation radius. So we don't know what exactly is happening and why exactly we see this cavity. And the most likely argument that we put as an explanation to this is a possible planet formation, which we are looking into, but we are not sure. So that's one of the main difference. Okay. And also the infrared characteristics are different. So hence the color diagram, the location of the targets would be different in the color diagram. So that's the reason we chose this diagram to, kind of distinguish between the transition disk and the full disk.
Okay, yeah, that's nice. So the transition doesn't mean it's into transition to the full disk.
Not really, no. Okay, nice. I don't know why the name was chosen.